So recall that the Bouligand stationary point is a point where the gradient of f of x bar transpose d is non-negative for all d lying in the tangent cone. That's what the definition of the Bouligand stationary point is. And every local minimum of OPT is a B stationary point of this. So regardless of what the constraint structure is, it might contain equilibrium constraints. That's perfectly okay, right? So it's okay to, so the structure of the equilibrium constraints stays within the specification of the tangent cone. I couldn't care less what it is. But it should be articulated that the tangent cone, articulating this tangent cone is indeed challenging when S is constrained by S is constrained by a set of complementarity constraints. So the way to deal with getting stationarity conditions when you explicitly characterize the constraints requires you to construct what is called a relaxed NLP. So the way we do that is that suppose we define active sets corresponding to which parts of the complementarity constraints are indeed active. So beta represents a set of indices where both components are 0. Alpha represents the components where yi is positive but fi is 0, and gamma represents the components where yi is 0 and fi is positive. Okay, so then the question is, how do you actually solve? How do you use this to construct a relaxed problem, right? So ideally, what I'd like to do, just so that you know where I'm going, I'd like to articulate an MPEC without these complementarity constraints. So these complementarity constraints, the per part, are the parts that lead to theoretical difficulties. They preclude you from actually writing down KKT conditions. So what you do is you say, okay, I'm going to write, if I know the active set at any x bar, I'm going to use this to relax the problem and only write equalities and inequalities but no complementarities. So this constraint relaxes this relaxes this. So when you have the point where you have joined, both of them are 0, you make sure that both y beta and f beta are non-negative, and in this one you just require that y gamma is 0 and f gamma is non-negative. Now of course if you get a solution of this, there's no guarantee that it's going to be a solution of the original. That's why it's called a relaxation, right? But what is nice about this is that it has some structure, allows you to write KKT conditions. Now you might say, well, what's the point of this? What's the point of this if it doesn't satisfy these conditions? I'm going to make that clear, right? So if P beta represents the set of beta 1s and beta 2, where beta 1 and beta 2 are index sets which are subsets of beta, but their intersection is empty, okay? So now what I'm going to do is, so if you look at this, this is alpha, beta, gamma, and now what I'm going to do is I'm going to define corresponding to beta 1 and beta 2. So we just look at this is the restricted NLP, okay? So let's distinguish it between the relaxed NLP and the restricted NLP. So in the restricted NLP, what happens is you have beta, which is this set, and corresponding to beta, what you do is you make sure that so here what you do, f beta for the whole thing is non-negative. Here f beta is actually equal to 0, and here y beta 2 is equal to 0, f beta 2 is greater than or equal to 0. Oh, sorry. Okay, so remember what beta is. Beta, both of them are equal to 0. So I want to make sure everybody understands that, because this is a bit subtle. Okay, so if I gave you a single complementarity constraint, let me just give it to you for a single complementarity constraint and you'll understand. So let's assume that this is, okay, let's talk about another one, Z and W. Okay, so this is the original problem. Now, if I'm looking at the relaxed NLP, so let's assume that consider a point x bar, let's call it u bar. U bar is x bar, y bar, w bar, z bar. At u bar, suppose beta, so let's assume that this constraint is 1 and 2. Beta is actually going to be the set of I. So actually let beta just be equal to 1 union 2, or rather 1 comma 2. So both of these at this, what you have is xy equals 0, x non-negative, y non-negative, right? So these are jointly complementary. Okay. Okay. So in this case, both of these are 0. So actually I should write it like this, I'm sorry. X is equal to 0, y equals 0. It just so happens that this is the origin. I just want to use this to show you what the problem looks like, what each of these relaxed problems look like, and what the restricted problem looks like. So let's consider the relaxed problem. In the relaxed problem, what do? In the relaxed problem, we write it as minimize f of xy okay. I basically relax this, okay, and if these are 0, doesn't matter, I just relax them, okay. In the restricted problem, I'm going to assume that so each of these, I'm going to assume that I'm going to keep one of these active, the other inactive, right. So I'm going to just say minimize f of xy x y equals 0 okay. So now what you have is, look, now is this a solution to the complementarity problem? Yes, but it's restricted. Why is it restricted? The reason it's restricted is because of the fact that now I've got, look at the way this happens, right. If I require that one of these is 0, the restricted NLP, what it does is it says y beta 2 is equal to 0, this one is greater than equal to 0, right. So it's just, and so now I'm going to use the two of these problems to articulate stationarity statements. So let's start by writing out the MPEC Lagrangian. Okay, so the MPEC Lagrangian, what it does is it writes multipliers for the inequality and for the y variable, the f variable, and the g variable, but it doesn't worry about the complementarity constraint. So for instance, and that's why it's important for you to, so you might say, why do you care? Well, you care because suppose you go and solve an MPEC, you need to know if the point you've got satisfies stationarity. For you to know that, you need to write out the stationarity conditions. To write out the stationarity conditions, you need to know what the Lagrangian is. And because it's an MPEC, it's not the standard Lagrangian, right? So when you have minimize f of xy so xy is going to be called z, okay. So the MPEC Lagrangian, what it's going to do is it writes it this way, f of xy, and now there's the perpendicular constraint, right, which is basically saying yi fi is equal to 0. This one I ignore. So when I write down the MPEC Lagrangian, I write down Lxy, I call this one eta lambda and mu. Okay, so I write Lx, or I just call it Lz eta lambda mu, and that's equal to f of z minus g transpose eta minus y transpose lambda minus f transpose mu. And notice I've ignored this one. Okay, I've ignored this. So this is the MPEC Lagrangian, and I'll show you how it makes sense. Okay. So now if you write down the KKT conditions using the MPEC Lagrangian, right, using the MPEC Lagrangian, these are the KKT conditions. Look, what you have is you have complementarity with respect to G, and then corresponding to each of these you use those active sets that I gave you. So let me just make sure everybody understands that. Bless you. So if I write down this, so gradient of y is just going to be 0 identity times lambda, and this is this is just gradient of f. This is lambda. Okay. And then you have complementarity between this. So you have 0 is less than g xy, and that's perpendical to lambda, not lambda. Which one is it? Oh, eta. Okay, so now the question is which of the y's are 0, which are greater than 0. So the y's that are 0, so remember what happens. I want to just make sure everybody understands how do I get the rest of these conditions. Look at this. This alpha free is because yi, oh sorry, I'm going in the wrong direction. Alpha corresponds to when yi is positive. So for those, when I take the gradient, what's going to happen is only the alphas will show up, right? For this one, so let me show you. Sorry, the alphas are 0 for that one. Right? Wait, hang on. Yeah. So here, lambda alpha is free. There's no lambda beta is greater than or equal to 0, and lambda gamma is equal to 0 because y gamma, the gamma indices are strictly greater than 0. Okay. So just so that you know, what you get is, so you have y alpha is equal to 0, which means that lambda alpha is free, y beta is greater than or equal to 0, lambda alpha is greater than or equal to 0, lambda beta, and y gamma is strictly greater than 0, which means that lambda gamma is equal to 0. Does everybody understand that? Because I know the active sets, right? What I've done is I know the active sets. I know which of the indices are active, which ones are inactive, and the betas represent those that are basically just greater than or equal to 0. Similarly, what you have is 0 is greater than f alpha, which means that the corresponding mu alphas are equal to 0. 0 is less than f beta, which means the corresponding mu betas are non-negative, and this is equal, which means that the corresponding mu gammas are strictly greater than 0. Is this clear? So what I've done is I know, so when I write down these KKT conditions, I know which are 0, which are strictly greater than 0. And as a consequence, when I write down the KKT conditions, I treat them either as inequality constraints or inactive inequality constraints. Inactive inequality constraints. So when I take the gradient, the multipliers are 0 for that. Yeah or no?
Sorry, I missed the explanation.
So what I said was, so normally if I were to take the KKT conditions of this, I would just take the gradient of this transpose lambda, right? But what I've done is, instead of writing the constraint like this, I've said y alpha is equal to 0, y beta is greater than or equal to 0, and y gamma is strictly greater than 0. So now when I write down the KKT conditions, this is going to show up, right? This is going to show up. So y alpha, when I take the gradient, this will show up in the gradient, and the lambda alpha is free because this is now going to be treated as an equality constraint. This is a strict inequality. So the lambda gamma is equal to 0, so this won't even show up when you write down the sum, and this will show up. Similarly, this won't show up, this index set, this one will, and this one will also show up. So what you've done is the inequality constraints have been replaced by actual equalities, strict inequalities, and just standard inequalities. Okay.
I need the explanation to why we know which is strict.
So we know only because that's at that point, any point you give me, if it's a so remember what we're trying to do. We're trying to establish necessary conditions of optimality. So when do we try and establish, at what point do we establish this? At the point where we have a local minimizer. So you give me a local minimizer. At that local minimizer, we know these KKT conditions have to be satisfied. The question is, how are they satisfied? Some of them will be satisfied as equalities, some as inequalities, some as strict inequalities. Given what so once you check that, you can check it. You can say, oh, alpha is 1 and 2, beta is 3, and gamma is 6 and 7 or something. When you do that, then you can sit and write down these conditions. Okay? So the way to do it is, suppose you run your algorithm. Why are we doing this? We're going to establish if the point satisfies the conditions. Suppose you generate an algorithm. That algorithm generates a sequence that converges to some point. Now you need to check for you to check if the algorithm has actually produced a stationary point, you need to go and check if these conditions are satisfied, right? And how do you do that? Well, at that point, you can evaluate the active sets, right? You have the point, you have x, y, z, you can check. Once you have that, you can automatically generate these conditions. Then you just have to evaluate them. Do you understand?
Yes.
Is that clear?
I don't know. I'm looking for the following after I see.
Okay, so basically this is just, if I give you a local minimizer, x, y, at x and y, you can tell what the active sets are and you can write down the KKT condition. This is an avenue to do that. And here is the statement. The statement is, if Z is a feasible solution of the MPEC satisfying a certain constraint qualification and some other conditions, then X is a Bouillon stationary point of MPEC if and only if there exists multipliers lambda, mu, and eta satisfying these KKT conditions. So what I've told you here is, under some conditions, a B stationary point is equivalent to a KKT point of some problem. Okay, it is not the original problem, it's some related problem. So I've related a stationary point of the original MPEC to the KKT conditions of a related problem. It's not a related, it's basically, in this particular case, it corresponds to the relaxed problem. Okay, corresponds to the relaxed problem. Now, there's also this notion of weakly stationary. In the context of weakly stationary, what you have is, if there exist multipliers corresponding to this, and here what happens is that this is exactly like the previous one, but you have a certain modification. I don't want to waste time on this one. This is just a. Let's talk about these stationarity conditions. So these are definitions. So now remember, let's just remind ourselves, B stationary. A B stationary point is a primal stationary point that satisfies the gradient of that point transpose D is non-negative where D lies at the tangent cone. Now, when you talk about stationarity in a primal dual sense, where you have the multipliers, there are various definitions, okay, based on what you impose. In this case, if mu I, okay, so let me show you this. Should be mu I and, one second, I just want to see which two and eta I. Mu and, oh, okay. So there's a, so when you see this here, this nu refers to the lambda here, okay. So I changed notation along the way. But the point is that if you have a degenerate, so let Z star be equal to X star Y star and D script star be the set of degenerate indices. Okay. So now, degenerate indices. So what is a degenerate index? So you may want to just remember this. A degenerate index is one where both yi and fi are 0. So if I tell you points where yi is equal to 0 and fi is equal to 0, it implies that I lies in the set of D's. So if you compute, if you have a point that is given to you and said, hey, here's x star, y star, you can go and check and see what the degenerate indices are just by comparing, right? Just check the yi's, check the fi's. If they're both 0, that's a degenerate index. Now, if you check the multipliers associated with the degenerate index, and if both the multipliers are non-negative, then this point is called strong stationary. Okay, let's make sure everybody remembers that. The mu I and the eta I. What is the eta I? The eta I is the counterpart of the lambda I that I had. I'm sorry, this notation changed here. So if the mu I is non-negative or the eta I is non-negative, so if both are non-negative, then it's strong stationary. If one is non-negative or the other is non-negative, then it's called astationary. If the product is non-negative, which means that both could be negative, then it's called C stationary or Clark stationary. And if both are strictly positive or 0, then it's called M stationary or Mordkovich stationary. Now, there's a lot of definitions here, right? And I gave them to you to tell you there's this, it's called the alphabet soup of stationarity conditions. For your purposes, focus only on strong stationary, because these are spurious, and the reason why they're spurious is that you can actually get a descent direction. So you know, normally if you have a stationary point, if you go in, if you try and take a gradient direction, even if it's a maximizer, you have to actually use something. If you use a direct a gradient type direction, the gradient is 0 here, so you can't move unless you use a negative curvature direction or something. Anyway, the point is that these three admit descent directions. You can compute a descent direction, so they're not really stationary. And this was observed after, and you know, there have been several people who've commented that the term stationary for this is misleading. But when you teach, it's important to give students the view of all the stationarity definitions that have been employed for this. So the ones you should focus on are strong stationary and B stationary. But there are lots of MPEC algorithms out there that might produce something that is C stationary. So if you run something in GAMS and you call an algorithm to solve a Stackelberg problem, try and go back to the code or to the theory to see what the guarantees are. Is it guaranteeing convergence to a B station, to a strong stationary point, or something weaker? If it's something weaker, like a C stationary, that point might not be a stationary point. You might be able to do better. Okay? Oh, sorry. Okay. So ACM and weakly stationary points allow trivial descent direction. That's why I didn't waste time on weakly stationary, and therefore less desirable. These are the relationships. If you're strongly stationary, implies you're B stationary. If you're B stationary, then you're strong stationary under the MPEC LICQ, which is an additional regularity condition. So these two are the ones you want to keep your eye on. B stationary doesn't require specification of the set, strong stationary does. Right? So if you're B stationary, then you're strong stationary under regularity condition, and if you're strong stationary, you're clearly B stationary. Okay? Now, I've got you a stationary point, so this is the way to articulate stationary points. And so from the algorithmic standpoint, if you generate solvers or if you're using a point that is generated by GAMS, it's always good to kind of assess if GAMS has not provided you with a statement of, sometimes the output in GAMS will tell you what the residuals are. But if it doesn't tell you, you need to check because you want to be careful. Okay. Now, another question is, does a Stackelberg equilibrium exist? Right? So this is a good question because often people take this for granted. Right? And if you don't have suitable properties, you don't have guarantees for this. So the way we prove existence is using the coercivity of the function. Right? So we try and show that a function, if it's coercive over the domain of x, then a solution exists. So remember the definition of coercivity. Definition of coercivity is if I go in any direction and if I go arbitrarily far away, then the function goes to plus infinity. So if I have a function like this, if I go arbitrarily far away, it goes up. It's bowl shaped. It needn't be convex because you could do this, right? Needn't be convex. Now this function, is it coercive? No, right? Because it could. I'm not sure what the left side is, right? If it's unbound on the left and it stays flat, it's not coercive. Right? So coercive functions in any direction should go to plus infinity as long as those directions are feasible. If they're not feasible, then it doesn't matter. Okay? So S is a closed and convex set and theta is a continuous and coercive function, then theta achieves its minimum on the set. Okay? So if it's coercive functions achieve their minima on closed and convex sets. That's an important result. Now remember, I haven't said anything about the non-convexity of that set. Okay? So clearly if there's no mention, then it's quite a general result. Okay? One second. Hang on a second. I thought I had this result. One second, okay? Oh, okay. Yeah, let me just state that for you. Yeah, so here I don't have the result. I'm not sure what I did with this result. But let me tell you what the result is. So the result that I'm going to leverage is the following. Theta x be a coercive function over S, where S is the set of x comma y such that x lying in x and y lying in C of x, or whatever, I think I call it S of x. But this is the solution set of a VI, and S of x is a solution set of a VI of an affine VI. So there are a host of results. One of the results that I'm going to give you is when an affine VI. What is an affine VI? An affine VI is one where the mapping is affine. So that's if under some conditions you can rewrite that as a complementarity problem. So VI mx plus q x is an affine VI. Where f of x is equal to mx plus q and x is a polyhedral set. Then if m is positive semi-definite, this should be theta xy. Theta of xy, if m is positive semi-definite, x is compact, and I'm trying to remember, then theta of xy achieves its minimum on this set. Let me actually have the book, because I was going to write this result down. Let me just check. There's one more that I have because I got this particular book along. This one has the result. So it's an obscure result which I don't use very often, but I thought it's worth noting. So I'll just state it formally, otherwise you won't have it. I want to make sure that you have it. Yeah, it's just this one. Yeah, I just need the continuity as well. So I just need, so this is coercive, I have that, and actually I don't even need this. I just need that f g gradient of f, gradient of g, and f be continuous. Okay. Yeah, this is the result. It's actually a little easier than the way I've stated. I've got, this is a weaker result, but let me give you the stronger one so at least you have the result. Be continuous. Let f script KKT be the set of KKT points denote the feasible region of MPEG. If there exists x0, lambda 0, sorry, y0, lambda 0, such that f of x0, y0 is greater, such that the set of x, y, lambda in f script KKT such that f of x, y is less than f of x0, y0 is bounded. Then MPEG has a solution. Oh. One second. Okay, so that's the result. Okay, so that was the result that I wanted to give. So basically what I require is, this is the MPEG, this is the function, G is the constraint, gradient of G is the gradient of the constraint, and capital F is the mapping. Remember the problem? This is the problem. G of xy is greater than 0, and then you have 0 is less than y is then f of xy. And fkkt is the other KKT conditions that come from this, right? So if there exists an x naught, y naught, lambda naught, such that the set of x, y, lambda that lie in this set, where this holds, so these are often called level sets, right? So it's like a sub-level set. If this is bounded, this set is bounded, then MPEG has a solution. Okay, so this is not, it's not absurdly hard to assess, right? So it's not particularly hard. And notice that this condition, you can also extend it to the stochastic regime by using, if your objective is expectation valued, not your constraints. If this is expectation valued, and even if G is expectation valued, you can go through the same process and get results for existence by just combining this with standard Fatou's lemma. You should be able to get it. Okay, should be able to get it. It's not too difficult. So that should allow you to deal with existence results for Stackelberg equilibrium. There are some other conditions you can get in the book by Luo, Pang, and Rolf, but there isn't much out there on. I mean, it's basically what you need to do is, it's a non-convex problem. If you have continuous functions, compact sets, you get existence. If you have coercive functions, closed and convex sets, you get, not convex, just closed sets are sufficient, you can get minima. See, look, it's on a set. This is not necessarily convex, it's just closed. Okay? Okay, so now we're going to talk about multi-leader, multi-follower games. Okay, so now we've reached the point where we can designate. So what did we do now? If you look at what we did, let me just write this. It's okay, I'll just do it here. Yeah. So now, if you look at what I just did, I said f of xi. Now suppose I have a situation where you have Stackelberg leaders that are competing in Nash. This routinely happens when you try and model generation firms that are strategic with respect to the system operator. So you have a generation firm that is a leader with respect to the system operator, but competes with other generation firms. So then you have a model that looks like this. You have a generation firm, generation xi, or the x1, x minus 1, and then you have y1, which is its follower decision. Okay, and all of them use the ISO's decision as, so the ISO is optimizing in y and parameterized by x, and each of them has its own, each of these guys have their own, I mean the models are identical usually, but not always, right? But each player uses its own conjecture regarding how the ISO responds. Okay, X. Okay, so these are called Stackelberg leaders. And this could be a single follower or it could be a collection of followers. Could be either. Okay, and so then this problem is captured as an MPEG. And now you have a Nash game between players that solve non-convex optimization problems, namely MPEGs. Okay, and so the question is, what is known about the equilibrium conditions of such problems? Okay, so let's look at this more precisely.
If there is just one ISO, would there still be y1 to yn?
Yeah, because when you solve and each leader solves the problem, then the leader's problem is going to use a particular variable for the ISO, and that variable is going to be y1. So now suppose I said that I want y1 to be equal to y2 is equal to yn, you could do that, but that's an additional requirement. You understand what I mean, right, Priyanka? So this, when I formulate the MPEG, remember what the leader does. The leader minimizes in her own decision, which is xi, and in yi, which is her conjecture of how the follower responds, given x minus I. Right? So you're going to get distinct yi's. Okay, so the set of players is going to be characterized as leaders and followers. Now the same player can be a leader and a follower if you're looking at sequential clearings. So if you're looking at competition in a forward market and then in a subsequent spot market, you can have players competing in the forward market as leaders and the same players compete in the real-time market as followers. Okay, so the players themselves can be leaders and followers. What we're really interested in is what the interaction is and when that interaction is occurring, and whether that interaction can be viewed as a responsive or a follower type interaction, or is it a leader type interaction. Okay, so then followers take the decisions with the knowledge of the decisions of the leaders, and in fact often parameterized by that knowledge. Amongst themselves, followers generally play a non-cooperative game. If there's a single follower, that follower just optimizes. Okay, leaders choose their decisions based on the responses of the followers to these decisions, as opposed to Nash. Right, in pure Nash, leaders just basically use the decision of it's the decision of its rivals that shows up only in terms of modifying its own payoff function or its own cost function. If you generalize Nash, then it affects your strategy set. So you can view this as being an extreme form of generalized Nash, where the coupling constraint that you have is actually a set of equilibrium constraints. And I'll make that more precise as we proceed. So here's an example. If multiple firms compete in the forward market, subject to an equilibrium in the spot market, firms broadcast their decisions, the spot market clears taking the firm's decisions for granted or given, and then in period 0, firms decide what decisions to broadcast based on the Nash equilibrium in the spot market and are themselves in Nash equilibrium. So they're competing in Nash. Okay. Is this clear? The framework? Okay. So let's provide a little more structure now. So now we have n script represents the index set of players 1 to n. It's a set of leaders. Each player is characterized by an objective phi I and a strategy xi. Assume the followers solve convex optimization problems whose Nash equilibrium is characterized by the solution set of a VI. We're just going to assume, in a generic form, players at the follower level solve convex optimization problems whose equilibrium conditions are given by a variational inequality. So that variational inequality is parameterized by the leader level decisions. Okay. So to give you an example, you can imagine that the spot market takes day ahead or forward decisions as given and solves, and reaches some sort of equilibrium. Okay. So now now this is important, this goes to Priyanka's question, right. So each player is going to have its conjecture of the follower level decision. Now what is interesting about this is that in practice, suppose we reach an equilibrium where you've got a set of followers like the ISO, right. So suppose Christy and I compete. Christy's belief is Y2 is her belief of the follower decision differs from mine. Both are equilibria, right, because if you write it out at equilibrium, what do we have? At equilibrium, if Christy's follower is solving Y1 in the solution set of VI of Y of X and F of f of x, okay, and mine is the same thing but it's y2. Now if there's a if this is strongly monotone and it's a unique solution, then y1 has to be y2, otherwise y1 need not be equal to y2. But from a physical standpoint, you have an equilibrium, right. So what is your thought? Do you think that we can implement an equilibrium where y1 is not equal to y2? And why is it relevant? Why is it relevant? So the first thing is that this equilibrium doesn't get implemented. What happens is that y1 harbors a belief regarding how the spot market clears. And similarly, Christy harbors a belief regarding how her spot market clears. We reach an equilibrium and her beliefs are encoded in the way she chooses from the solution set. Now you can have an additional mechanism for selecting from that, right. You could do that if you so chose to do so. Or you could in some sense decide that I'm going to regularize the follower market and get rid of this lack of uniqueness, lack of non-uniqueness, I apologize. Okay. You could do that, but in the absence of that mechanism or in the absence of that regularization, y1 need not equal y2 at equilibrium. Okay. Is this clear? This is important. Okay. Now let me ask you another question. If y1 is not necessarily equal to y2, do you think that this could be viewed as a shared constraint? Because look, the VIs are the same. Look at this. This VI is the same as what y2 will see. Both will see x, right? What is different about these VIs? I mean, is there anything different? How would you change this problem to make this so first of all, this is a generalized Nash game because strategy sets are coupled by competitive rival decisions. How would you make this a shared constraint game? Any thoughts? And I'll go into this later if I have time. It's not a shared constraint game, right? Because look, your decision is y1 and my decision is y1, Christy's decision is y2. So we have different decisions and they can, so in some sense her decisions are not encoded here.
Remove i's from y.
Remove what?
Make y common to everything.
But if you make y common to everybody, who chooses the y?
Like,
We find somehow a way to connect all the leader decisions and enforce that connection across all the.
So how would you do that? So that's a good idea and that's exact, but how would you do that? How would you, not the leader decisions, right? It's the follower decisions. How do you make them, so one question is that you don't need, so what happens if y2, if Christy comes up with y2 and I come up with y1? At that point, essentially the constraints that she sees are different from the constraints I see, right? Because at equilibrium, her constraint is given by that equilibrium constraint where y2 lies in something. It's a different solution. Mine is a different solution. The way to do that is to replicate hers so that the y1 is in hers and the y2 is in mine. So which means that you can modify this. Now this is a modified game. So this is 1 and then I can put a y2 here as well. The same thing. Now this constraint becomes a shared constraint game. Okay? And I'm going to show you that this has some benefits. Okay? It turns out when you're solving EPEX, for those of you solving EPEX, this avenue is actually a very beneficial avenue to get solutions. How many of you solve EPEX? Many of you are solving EPEX? Not yet. So when you solve EPEX, you'll realize that EPEX, the algorithmic development is very poor. We just have not been able to crack the problem. It's a difficult problem. We don't have convergence theory for solving these problems unless it's a very stylized, like a potential game or something of that sort. As a consequence, often if you run naive algorithms which are like best response type updates, you have cycling occurring. So one avenue that tends to obviate cycling is using the shared constraint structure. Okay.
So here, what do you mean by yx? Do you take the set of both the...
So y of x you mean? What do you mean? You mean y1 or y2? What do you mean? You mean y of x?
Yeah, I mean, what have you modified here? I mean,
Oh, I've just replicated both of these. So you know just how you have yi there? Then you should have yj for all the other players as well. So instead of having only one equilibrium constraint, you have n equilibrium constraints. Bless you. Okay, I'll do more of that later. So I'm going to write that out.
and does the leader then optimizes with respect to not xi, but not just yi, but all y's
No, it takes y2 to yn as given,
as given?
right? So now, anyway, let's go ahead and do this, and I'll go to that later if I get a chance. I want to. So now you have xi and yi are closed and convex sets. Let omega I, xi, x minus I, y minus I be the feasible region of the leader, and omega be the Cartesian product of these set valued maps. Okay. Let f script be the set of xi such that xi yi lies in this. It's the set of fixed points of omega. Remember what omega is? Omega is the counterpart of what I had in the generalized Nash game. In the generalized Nash game I had, remember in the generalized Nash game I had so in the generalized Nash game I had this structure. Minimize theta of xi x minus I, xi lies in xi x minus I. In the case of the multi-leader multi-follower game, I have minimize fi of xi x minus I yi, and then what I have is xi yi lies in omega I x minus I y minus I. Okay. This is the feasible region. Okay. So this is the counterpart of this. Now in the generalized Nash context, I assumed that this mapping, this set valued mapping, was closed, convex, There's a set valued map but it's closed and convex. Can I make the same claim here? Can I claim that omega of x minus I is, can I claim that this, the image of this under the mapping, so basically is this, does omega I given x minus I and y minus I spit out a convex set? It can't, right? Because this is a complementarity constraint. I mean, it's a non-convex problem, right? Given x minus I and y minus I, it's a solution to some variational inequality problem, right? It's not convex, right? By itself, it's not convex. Now, it should be said, so there's been one effort which people have tried where if I knew that the solution set is compact, the solution set of the variational problem is convex, if you have a way to characterize a solution set without writing down complementarity conditions, then you might be able to get around this. Because think about it, if you magically knew this was just a convex set, and you know that when the mappings are monotone, you know the solution set is compact, you just have no handle around articulating that solution set. Okay?
So compact or convex?
I meant convex, I'm sorry. Yeah. It's also compact, it turns out, but compact is not relevant. What is relevant is convexity, and actually closeness is relevant, right? Okay, so this is the feasible region of Li x minus I. F script is xy such that xi yi lies in this, right? So basically what you notice is F script represents a set of fixed points of omega. This is an important insight. When I get an equilibrium of this problem, at equilibrium, what do I have? At equilibrium, I have xi, yi, so I have x1, y1 lying in. So this is an important, at equilibrium, I have x1, y1 lying in omega 1 x minus 1 y minus 1. Okay, xn yn lying in omega n, which implies that x comma y lies in the Cartesian product. This is omega xy, which is defined as the Cartesian product Okay, so what is this? This is a fixed point problem, right? So if I get an equilibrium of the multi-leader, multi-follower game, that equilibrium you're looking at over the set of fixed points. These are all the feasible solutions, and you're looking at a problem where you're trying to select from the set of fixed points a Nash equilibrium. Okay, does everybody see this? Irina, is that clear? Arno? Not clear? Okay, so let's go back to this. So if you're looking at this problem, this is the agent problem for the multi-leader, multi-follower game. All the nastiness is encoded here. The second level problem, everything. At equilibrium, what do you need? You need to make sure you're going to have feasibility. Do you agree? So if you have feasibility, you have this holding. You have this holding for all n. If it holds for all n, if you put this as a vector, this holds for x and xy lying in omega xy, which is the Cartesian product of these sets. But that's like saying this is the fixed point. So if it's the fixed point, what we're saying is I want any feasible xy, any choice of xy from the Nash equilibrium has to be selected from the set of fixed points of this. Right? These are the only feasible choices for the Nash equilibrium problem. One of these, some subset of these satisfies the Nash criterion. What is the Nash criterion? That at any agent I have no desire to so unilateral deviations are unprofitable. Okay? Do you see that now? Panush, what do you think? Anna, is that clear? Do you see this? So what I said was, so first of all, do you agree that the only points you need to look at when you look for Nash equilibria are fixed points of omega of xy, because if you're at equilibrium these have to hold. So if you're working in this set, all you need to do is find an xi you need to just find an xi yi I equals 1 to n star that lie in the fixed point of omega such that the Nash criterion holds, which is xi star yi star is less than, x minus I star is less than f of xi yi xi star for all xi yi in the fixed point of omega, right? If that holds for all I, it satisfies the Nash criterion. So I just need to look around this in the set of fixed points. Now that's harder. The only reason I bring that up is it's a way to characterize this problem. It's a problem of selecting from the set of fixed points of omega of x. Do you see that now? There's something you don't see, tell me, I'll go through it again. Right? So I've got the set of, so this is going to be selected from the set of fixed points of omega, and this has to satisfy the Nash criterion for all I. So I want an xi star, yi star, such that given x minus I star, I satisfy this for all other points in the fixed point, all other fixed points. Because the only feasible choices are fixed points, right? If I'm feasible, I have to be at a fixed point of omega. But when are all feasible points Nash equilibria? No. The only ones that are Nash equilibria are the ones that satisfy the Nash criterion. Clear? Antonio? Emily, what do you think? Clear? Okay. Okay, so then I refer to these set of fixed points as f script. Okay, so if I refer to the set of fixed points as f script, and I'll use this, right? So look, I essentially have this here. By a leader-follower Nash equilibrium, I just mean a tuple of leader-follower strategies xy from the fixed point such that xi yi is better than ui vi for all ui vi lying in this. Now remember, at equilibrium what happens? Xi yi has to lie in this, which means xy is a fixed point. Okay. Now for followers in the Nash followers are in the Nash equilibrium given the strategies of the leaders. For leaders, no incentive to deviate from xi yi to any other strategy in this set, right? So that's why we have this notion of an equilibrium program with equilibrium constraints. The equilibrium constraints come from the follower reactions. The equilibrium problem comes from the fact that players are competing in Nash. Okay. It's an optimistic formulation because I'm minimizing both in x and y. If I was minimizing in x and maximizing in y, it would be a pessimistic formulation. Yi's are mere conjectures. At equilibrium, we may have yi is not equal to yj if yi has non-unique solutions. That's important to recognize. If you solve this problem and you have two agents who are doing it, one agent might have a different understanding of how the follower reacts compared to the first. Okay, what that means is you might have different flows. It's possible. There's no guarantee, right? There's absolutely no reason why the ISO should have unique solutions. Now, the EPEC is an extremely relevant problem, and the single leader case is well understood. What is the single leader case? It's just the MPEC. It also shows up in mechanism design problems, a host of other problems. The existence of equilibria in the multi-leader case remains an open question. Okay. Now, what Zhongxi-Pang and Masao Fukushima showed in 2005, very simple EPECs fail to have solutions, okay, which for us is very disconcerting, right? So imagine this very simple EPEC, half x1 plus y, half x2 minus y. This guy is, they're both minimizing, and this represents the optimality condition of a very simple problem. You can see it, it's just it's on a non-negative orthant, you're just looking to minimize, you know, this, and the follower, the solution is given by this this equilibrium. The solution of the follower is given by this. Now, what is interesting about this problem? What is interesting about this problem, and I'm going to go back to it later. You know what I told you about adding extra constraints from the other followers? What we recognized in some of our previous work is that the big problem here is that it shows up that basically two different players have if you have two different conjectures of the follower decision, you end up with non-equilibrium. That's one of the reasons. But if you make them consistent, equilibria emerge, and I'll show you that at the end. Okay. Now, most of the work in this area has been model centric. So, for instance, amongst the earliest papers was by Hanif Sharali and in 1983, where they looked at a sequential game where where players compete in Cournot in two consecutive settings. It's a very stylized problem, and so for those of you thinking of proving existence, right, let me tell you how existence was proven there. There what they did was they were able to show, they were able to get a structural form for the solution to the follower problem. Once they did that, what they did was they eliminated this and they wrote this as a single valued map. Now, this wasn't a smooth map, it was non-smooth. But even if this is a non-smooth function, they were able to then use fixed point arguments to get existence, right? So that was one thing that they did. Hobbs and all in Hobbs, Metzler and Pang modeled one of these generation and ISO problems as an EPEC, but they didn't look at existence results. De Miguel and Xu again used, they also used elimination of the follower level problem, okay, with Xu. And then Danny Ralph with Shimin, who looked at similar frameworks, and Chelin Su actually extended the work by Hanif Sharali when they looked at agent specific cost. There's also some related work by Utrata. We also have some results which I'll point out at the end where we have some existence results, but for a stylized problem. Okay. One of the big challenges is that we don't have an understanding of the mathematical principles that this equilibrium rests on. And so we spend some time trying to do that. So I want to kind of give you some ideas about that. So what is the classical approach for looking at the existence of equilibria? So the classical approach has been using fixed point arguments. Brouwer uses maps which are convex valued, right? Now you have Kakutani which uses, but Brouwer's fixed point theorem requires single valued maps, right? So now the problem is that when you have set valued maps, what do? Well, Kakutani's fixed point theorem allowed you to do that, but it needed the sets to be convex. Problem here is it's even worse because they're set valued and they're non-convex. So there is a fixed point theorem called Eilenberg-Montgomery which allows you to deal with some of these, but a direct application is not possible. I mean, there's mathematics that we need to develop to deal with it. We don't have it yet. So from first principles, what you want to think about is what is the reaction map? What is the reaction map? When does an equilibrium exist? The equilibrium to a Nash game exists when you can analyze the best response map, right? And if that map has a suitable, or the reaction map has a fixed point, you're done. So what is this reaction map? Reaction map is also the best response map. Given what everybody else is doing, what is the best thing to do? Now, if you're at a fixed point of the reaction map, you're at a Nash equilibrium, right? So now the question is, this reaction map, if you can analyze it from the standpoint of fixed point theory, then you have a hope. The big problem is the reaction map is extremely nasty. You expect it because this minimization is over a non-convex problem, right? Not just a non-convex problem, it's a problem which is complicated by equilibrium constraints, So it's incredibly nasty, right? So to get an understanding of that set of reactions, that set of reactions may not even be connected. Forget convex, may not even be connected. Okay? So you could apply fixed point theorems, but fixed point theorems rely on the following. It needs to be a self mapping. What is a self mapping? A self mapping is a mapping so the mapping has to map from the set C to a set C. Okay? The mapping is required to be continuous or a weaker form of continuity called upper semi-continuous. Not true in general. The mapping, the domain of the mapping and the mapped values have to be of a specific shape. Convex, a weakening of convex in topology, there's something called contractible, which is a weakening of convex. Right? So there are ways that you can kind of deal with some of these weakenings, but still, we don't even know if these things hold. In our case, our reaction map is not a self mapping. The continuity of R script is notoriously hard to get, needs continuity of omega, don't have that. Okay? It's hard to say anything about the shape of the domain of omega, right? Now, the idea is that if omega is a shared constraint, the problem is that omega, look at omega. In our case, omega is not a shared constraint, right? Omega in this case is just a feasible region, it's not a shared constraint. Turns out that when omega is a shared constraint, right, if uv lies in omega of xy, so what is a shared constraint? If uv lies in omega of xy, it means that uv comma xy lie in some set. Remember what it means to be a shared constraint map. If I tell you, and I did this in the case of generalized Nash, in the case of shared constraint in the generalized Nash case, I said if xi lies in xi of x minus I and it's a shared constraint, this is equivalent to saying that xi x minus I lie in some set C, some fixed set C. So if I can show or if I can construct a shared constraint version where this lie in some other set F script, then I might be able to do something. Okay? So define psi, where psi maps onto f times f, and epsilon, which maps is a set valued map from f. You can actually write epsilon as taking x comma y and x bar y bar as this summation. So what it does is it takes x bar y bar I and x minus I. And epsilon basically takes the set of x bar y bar in f where psi is equal to the infimum of over the set of fixed points. Okay, so I don't want you to spend too much time looking at the details of this, but I want to just tell you what we did. Okay, it turns out that if omega is a shared constraint, then every fixed point of epsilon is a fixed point of R. So if I get a fixed point of some other map, I've got a fixed point of the reaction map. This was something that was observed earlier by Rosen, and the good thing is that this map is upper semi-continuous. It's easier to characterize even though it's non-convex. Okay? The problem is that this is not a shared constraint game, right? That was something that we know. The thing is, can you provide modifications of Li that result in a shared constraint game and present a paradigm for analyzing equilibria with shared constraints based on topological fixed point theory? Right? I don't want to, I'll see how much I have here because this is something that was, it's a little different, right? So what are we doing? I gave you the original EPEC. I have some weak results at the end for that EPEC. For the more general EPEC, we don't have results. It's an open question, right? That's something people have been looking at. And one avenue that we've looked at is to look at a nearby problem and say, does that nearby problem, and when we say nearby, we haven't qualified nearby. What we'd also like to do is, we'd like to relate them, and we haven't done that. So there's still holes in this theory. This is very recent, right? But I want to show you what is available, right? Because these are hard problems. Okay, and it's also, these are good research questions. So if you're looking at research questions, this is, so EPECs bear close resemblance to shared constraint games, but they're not shared constraints. Because The reason is, and this goes to the point you made, yi is a decision way of leaders i's problem. It's not related to yj's, right? Now, omega is a shared constraint if we have this holding, but that doesn't hold, right? For non-shared constraints, we have that this holds, some c script I, right? So the space of permissible strategies for each for the game is different from the point of view of each agent. It's not the same, right? So this is often called the abstract economy by Arrow and DeBrew in their paper in 54. Okay. So here is one idea that we came up with. So suppose we say that we replicate everybody's equilibrium constraints at a particular for each agent. So then what happens? Given y minus j, now you actually have a shared constraint. This is independent of I. So look, this is omega I A. A is all equilibrium is equal to something, and now what you notice is that basically all of this lies in a set which is independent called G. Okay, it's a fixed set, right? And what is that fixed set? That fixed set basically is some intersection of the fixed points, the set of fixed points, but it's a fixed set for a map. Okay, so f script A is, so now if you can, and now what you have is this E script AE represents this constrained epoch. It's got extra constraints. Now how do you relate equilibria of the original problem to this problem? Well, we can go in one direction. If I have equilibria of the original epoch, they're equilibria of the new epoch. So if you solve the new epoch, and we haven't done this yet, we don't know how to do it. If you had a way of selecting the right equilibria from E script AE, you'd get equilibria of this. We don't know how to do that yet. What we do know is that this newer problem contains equilibria of the old problem. The hard question is coming up with equilibria and selecting the right one, somehow pivoting and moving, but we don't know how to do that yet. Okay, there's another way to do this, okay, using what are called consistent conjectures. So I just require that all of the yj's are equal to one of them. Everybody puts the same constraint. Okay, and once I do that, again I get a shared constraint. Okay, so if S is single value, then every equilibrium here you need an extra requirement of E is an equilibrium of ECC. Okay, so does everybody understand what we've done? We've been able to show a relationship. Now you might say, okay, you've got this with a shared constraint. How does this help us? How does this help us? Okay, so one thing, before I continue, I want to show you this. That a constraint is shared does not imply that the conjectures are consistent. So you want to understand one thing. Just because I solve this problem with, suppose I solve this and it's a shared constraint, does it mean that at the equilibrium y1 is equal to y2 is equal to y3? Not in this case. I could have different y's, right? But in this case, yes, I have the same y's. Okay, so just because the equilibrium is shared doesn't mean the conjectures of the follower equilibrium are the same. They're only same if I enforce that. Okay. Yeah.
But sorry, why did you do that? I mean, why did you make all y equal?
There's a different way of doing it. We just gave two ways of showing that you get two different types of shared constraints. So in each case, it results in a shared constraint, right? So remember what a shared constraint is. A shared constraint is a constraint that satisfies this property. And I wanted to show you two different ways of getting a shared constraint. But they lead to different requirements. In this requirement, at equilibrium, all the y's are identical. In this one, the y's might be distinct, but they all show up as constraints.
And you still retain that constraint in the next module also?
This yj and sx? No, I just have y1, yj equals y1.
Or yi belongs to?
Yeah. So basically, every player has to have all of these constraints. So every player has to be constrained by the fact that y1 is equal to y2, so. Okay. Now, yeah.
Is this looks to me somehow some form of non-anticipativity across the different.
Yeah, it's almost like a non-anticipatory type constraint that you see in stochastic programming. It's a bit like that. But the rationale for imposing it is different. The reason we introduce non-anticipatory constraints in stochastic programming is because we're using decomposition. And once we use decomposition, we need a way to kind of solve these problems in parallel, right? Okay, so let's look at some special cases of existing models. So what I want to do is, let's move past this. So let me show you an example. You remember the example I had with Fukushima? So in Fukushima's example, the big one by Pang and Fukushima, this was the one where we didn't have existence. Okay, and now what we do is, if you look at the reaction maps, this is the reaction map of X for player 1. So given x2, this is what you end up doing for all x2 and 0, 1. The reaction map is 1 minus x2. The reaction map of this is the reaction map of x of 1 and given x2. This is the reaction map of 2 given x1. Now remember what we need. We need a fixed point of the reaction map. It turns out that this, and that's why this problem doesn't have an equilibrium, right? The overall reaction map doesn't have a fixed point. Now let's modify it. It's not a shared constraint game. Let's add this extra constraint. So all I've done is I added all equilibrium constraints. As soon as I do that, this becomes a shared constraint game. And when it becomes a shared constraint game, it's a different game. But it was interesting to see that for this game, you're able to actually show this is what the epsilon is. This is the psi. This is the epsilon. This is the map that we're looking for. And what we do is that we can actually from this get an equilibrium for this problem.
Equilibrium of the new problem.
New problem. And what is interesting now, you want to be careful, right? So we don't want to kind of spuriously add equilibria to problems. We don't want to do that. But when problems our contention is that some of the epochs are not very well posed. So when you have practical problems which don't have equilibria, it suggests to you that the modeling there's something in these models that prevents you from, and so the question is it that when you try and solve practically occurring epochs, and because you don't have a shared constraint structure, are we seeing, because in a simple setting we saw that you didn't have a fixed point and we couldn't get a solution, and you have cycling occurring. The question is that is this issue more widespread than we realize? We don't have a way to assess that. But what we are seeing is that if we take practically occurring epochs, we can prove that at least in simple cases where you have had problems, equilibria emerge. And remember, this is not a question of saying that, well, you just modified the problem. The problem is that we believe that this modification actually has some intuition. What it does is basically allows you to introduce some structure into these problems, and in some sense it makes the problem better posed. Okay?
So you generated a new equilibrium with the shared constraint.
Yeah.
Okay? And that one has a
yeah.
Okay, fair enough. But what does it say about the original one?
The original one doesn't have it. So what the contention is that the original one, I believe, this is what, and because these are hard problems, it's hard to say. If you have a problem which doesn't have an equilibrium, it's very hard for you to kind of say something about this equilibrium from a welfare standpoint because the other one doesn't have an equilibrium. Our contention is that some of these problems are just not very well posed. Because of the structure of these equilibrium constraints, you're precluding the existence. If in a two-variable case, if you're losing existence, imagine what's happening in more general cases. And so I wonder whether the root of this is something in the shared constraint structure and the way we model these.
But we can't say anything about the original one.
The original one in this particular case doesn't have an equilibrium. I mean, this was a spurious. Yeah, you can't say anything. I mean, this had no equilibrium. You can't. Now, what would be interesting is if you can look at problems for which you don't know if an equilibrium exists, and you can show this one exists. So what we can show is, in general, when you add these constraints, an equilibrium of the new problem, equilibria of the old game lie in the equilibria of the new game. Now, if you get an equilibrium of the new game, it may or may not be an equilibrium of the old game. Like in this case, the equilibrium of the old game did not have any, the old game did not have equilibrium.